Hello, welcome to this lecture number 3 of week 1 in the course on control engineering. We started off lecture 2 by looking at some characteristics of systems and classified them as either static or dynamic. So we go a step further and classify them further. So as always, we will motivate ourselves through some examples. And we all understand simple circuits, resistive circuits, nothing complicated. So, suppose I start here with a simple resistive network. I have two voltage sources V1 and V2, some resistors, and I'm interested in what is happening across this resistor R2. Okay, so I just do my simple math, or I can just do a PSpice simulation. I can easily compute that the current through R2 is just 4 amperes. Okay, I do something else now. I do not consider the effect of V2, I just short it. I just consider what happens if only there is V1. And I compute the current turns out to be 2 amperes. Then I do something similar, I get rid of V1, I short it, I have V2 which is 7 volts, and the current through R2 only because of V2 is now 2 amperes. So I add this and I add this and I get the total is 4 amperes, which is exactly what I have here. Okay, it's as simple as saying that okay, so I have say I'm filling if I look at our tank example, let's say there are two inputs. So say 2 taps Q in. So this is say Q1, Q2, and say water is filling through the tap into the bucket. So if I say that I have Q1 and Q2, the total water will be the effect or the net water supplied by Q1 and the net water supplied by Q2. So if I have both taps on together for a minute, or I switch on tap 1 for a minute and tap 2 for a minute, I think the net effect will be just the sum of both of them individually. So similar thing is happening here, right? So current due to both sources V1 and V2 is equal to the current only due to V1 plus the current only due to V2, and this is called the property or the principle of superposition, which says that if I have a circuit with multiple current or voltage sources, the total current or voltage can be determined by computing the voltage or current of each of the sources independently and summing them together. So even if I have say 2 voltage sources, 3 current sources, I look at the contribution to each of the individual voltage sources plus each of the individual current sources, add them up to get the net effect. We can also look at it in different domains, right? If I look at a beam, and if I have load on the beam, the beam which is now like this will see some amount of deformation like this. Okay, what this means is that the total deformation of the beam under multiple loads will be the sum of deformation caused by each of the load. Maybe the first load causes a smaller deformation, second one maybe something like this, and the third one something like this, and the overall can be maybe you can see the net effect of the total deformation. So sum of each of the deformations caused by each load independently. Also, if I have say I have a charge and I have some kind of an electric field which is okay, not drawing the best of pictures, but the electric field at a point due to multiple charges, if I call this as E, is the vector sum of, say, this is the field produced by the charge E1, this is the field produced by charge C2, and E2, Q, and so on, right? So this is the field produced by say a charge Q1, charge Q2, all the way till say charge Qn. So the total electric field is just a sum of all the individual contributions. Okay, this is nice. This essentially is again, I'll repeat, this is the principle of superposition. Okay, what next? Okay, so I do the same circuit, still have 28 volts here, I have 7 volts here. What I do is I scale the voltages by half. So what was 28 now becomes 14, what was 7 now becomes 3.5. Just like the same thing, right? So if I have two taps feeding into a bucket which is filling water, I reduce the quantity, or the knob which was open fully, I will just open it by half. So the net amount of water that will flow through is halved, right? So earlier if it was Q in, Q1, now it was just Q1 by 2. This will be Q2 by 2. Okay, what is the effect of that? We'll see what happens with the current. The current which was originally 4 amperes is now 2 amperes. So V1 is now V1 by 2, which is 14, V2 is V2 by 2 is 3.5. The current also reduces by half. Similarly here, right, the amount of water which I was pumping in originally with flow Q1 and Q2, and now if I am pumping those with Q1 by 2 and Q2 by 2, the amount of water will just reduce by half. Okay, which means that if the input voltages or even currents are scaled by half, the output current is also scaled by half. Okay. Now this could be generalized to any factor. If they are doubled, if they are tripled, if there is not just half by or 1/3 or 1/4. So if the input is scaled by a certain factor, the output also scales with the same factor. You can also look at it in different domains, right? If I just say F equal to ma, if I double the force, the acceleration also doubles. Okay. Similarly, I know that a capacitor stores a charge based on a certain voltage, right? If the voltage is double, the amount of charge is also, if the voltage is halved, the amount of charge halves, and so on. So when there is a certain scaling in the input, the output also scales accordingly. Of course, things will be different when I just scale this to 14 and leave this as 7. It will not work as it is. So all the sources should go down by half. Okay, nice. So this is called the principle of homogeneity. Right? So two things we learned now. One is superposition. Second is the homogeneity. Of course, since I said that we will kind of use the language of math to communicate or write down things better, all what I said can be written down simply in a very nice expression like this. So f of a plus b is fa plus fb, right? So this is I could look at it in several examples and check. So let me say, I'll just do a simple thing. So I have, say, a system of the form, say y is m times x. Okay, then I have, let's say, instead of I have y1 is m times x1, y2 is certain m times x2. If I just say, okay, what is now, if my input is just x1 plus x2, what is my y? Y is m times the input. So m times this new input will be equal to m x1 m x2. This is y1 plus y2. So in the more general case which I wrote, this is f a plus b. That I am looking at the output is a function, right? This is so this is my y. If I look at f a plus b is, if I write it, this is what is this? This is simply f of a plus f of b. Okay, so this superposition. Okay, now I take a circuit V equal to L di by dt plus R times I. You know this is like I am just writing down equations, the voltage laws for a system which has a R, a L and an I. Okay, is this linear? Let me say that what happens when I have so again I have to check the applicability of this, right. F of A plus B should be equal to individually F of A plus F of B. Okay, so if I say that I have say V1 will be L di1 by dt plus Ri1. Okay, this is input output relation V1 producing certain I1, and the V1 and I1 are related via this equation. Similarly, I do V2, this will be the same L, right, the L and R don't change, the circuit is the same, instead now I am applying two different voltages resulting in two different currents, di2 by dt plus Ri2. Okay, I add these two, this means that I have V1 plus V2 will give me L di1 by dt plus Ri1, L di2 by dt plus Ri2, this is L d by dt of I1 plus I2 R I1 plus I2. Okay. So, V1 results in I1, V2 results in I2. What does V1 plus V2 result in? V1 plus V2 nicely beautifully results just in I1 plus I2. So, V1 plus V2 gives me the total current of I1 plus I2. So, I can say that superposition holds here as well. Okay, this is also nice. Let us see what the other examples are. Okay, maybe I will just put another example here also. Let us say I have an example, say y equal to cos of x. Okay, let us start with example first. Say y is cos of x. Because of x1, the output will be cos of x1. Because of x2, the output will be cos of x2. Now, if I apply both the inputs together, x1 plus x2, and what is the relation between input and output? That is the cos. Okay. Now, this is not equal to cos of x1 plus cos of x2, and therefore, this is also not equal to y1 plus y2. You can say therefore that there is no superposition here. Okay. So, the thing that we learned, right, that if I reduce the voltages by half, the current reduces by half and so on, it is not holding here. Similarly, I have what is the other example here, Gj plus, okay, so W equal to G times J plus what was that, M dJ by dt whole square. Okay, I'll write it a little better. Okay, where this W and J are like functions of t. Like similarly, what we had at analogous to, in some sense, V equal to Ri plus L di by dt, just that in now I have a square term here. Okay, so W1 is the input which gives me an output of J1, and then W2 is the output, sorry, if W2 is the input, so W1 gives me J1, and similarly W2 gives me J2. Okay, if I do W1 plus W2, this is G J1 plus M just G J1 plus G2, okay, this is fine, plus M. Now I have D J1 by dt the whole square, D J2 by dt square. This is not equal to, so what I would expect, right, if W1 plus W2 should produce an output current, or alas, does it produce an output current J1 plus J2? If it is doing that, then W1 plus W2 should just be related by this relation. So I should have G J1 plus J2 plus M d over dt of J1 plus J2, the square of it, okay, and this is not, this term is not equal to this, and therefore there is no superposition here as well. Okay, so two examples here, that there are some cases where superposition holds, some cases where superposition does not hold. Okay, mathematically, what is homogeneity? A function is homogeneous if, what we said, if I scale the input by certain factor, the output also should scale by a certain factor. Mathematically, it would mean like this, right? So if I have f t x comma ty, where x, y were the original, say if I may call that as input and output, if I scaled it appropriately, say I had V1 and V2, right? What did I do to V1 and V2? I simply have them V1 by 2, V2 by 2. They should satisfy a relation like this. Okay, mathematically what it means, if I just take this example here, and if I say I just double the f of 2x, f of 2y will be, what is this? So this argument, if this is an x here, is x square, if it's y, it's a y square, so 2x square, 2y square is 4x square plus y square. What is it? This is 4, 4 is 2, which is the factor I took here, the scaling factor, 2 square. What is this? X square plus y square is simply f of x comma y. Okay, so this is a homogeneous function. What happens here? I can simply check here. So if I just do f 2x 2y, this is 4x square 4y square plus 4, and this I cannot write at any factor, 2 square x square plus y square plus 4. This is not equal to this, right? So this is not homogeneous, this function. Okay, now I see some input output relations or systems which satisfy both superposition and homogeneity, and some which do not satisfy superposition and homogeneity. Okay, so this you can see there is some classification here. Then we can put everything which satisfies homogeneity and superposition in one basket, take the others which do not satisfy, put them in another basket. Now we have two different categories, and let us give them some name. Okay, so the first thing is, we will call the systems which satisfy both superposition and homogeneity as linear systems. So any linear system will satisfy principle of superposition and homogeneity. There are few more properties which we will see a little later, but for now, any system, the linear system is something which we will say it satisfies both superposition and homogeneity. Nice. Okay, how do I write this pictorically, right? We will kind of write down some nice block diagrams. This is also a little nicer to visualize. Okay, what superposition says is that if I have a input x1 which causes an output y1, input x2 which causes an output y2, I sum both of them to get y1 plus y2. Instead what I do, I don't sum them here, I sum the inputs. Instead of feeding x1 individually measuring y1, x2 individually measuring y2, summing both of them here, I just say, okay, why not just feed x1 and x2 both together. If I feed x1 and x2 both together, if I just get as the output as y1 and y2, if these two agree, then I say that the principle of superposition is satisfied. If they do not, then of course not. Then you can look at our other examples also what we did. Homogeneity is the same. I take the input, I measure the output, I scale the output by some factor k to get k times yt. Okay, I mean just take input, output, put some scaling. Okay, just like here I said, why not I add to both the signals before? I say, okay, why not I just take this guy and put it here. Don't feed xt to the system as input, feed k times xt. And if the output is k times yt, then you say, well, this is homogeneity. Both things were working here in these two examples, here and here. Okay, so this is another way of maybe pictorially or diagrammatically representing linear systems which satisfy superposition and homogeneity. Okay, question for you. I take some other system y equal to mx plus c, input output relation between from x to y, where x and y are related to this. Does this satisfy superposition and homogeneity? Quickly check that. Okay. Now we said we had two things. So what is a linear system? It should satisfy homogeneity plus superposition. I'll just use some abbreviations here. Is yt equal to cos t xt a linear system? Okay, fine. I'll take x1 of t, sorry, I take x1 of t, I multiply it with cos of t, I get y1 of t. Okay, good. I take similarly x2 of t, multiply it with cos of t, I get y2 of t. So I just sum both of them here. Now what I do is I just sum, so this is my output here, right, which we were measuring here, y1 plus y2. So this will be now cos, no, what was that, cos t x1 of t, right. So this is cos t x1 of t, this is cos t x2 of t, and I sum them, I get both cos t x1 of t plus x2 of t. Okay, so instead now what I do is I give input as x1 of t plus x2 of t. How does the transformation happen from input to output? Via this term cos t. So this what does this give me? So this is equal to, since this adds up, or this distributive law for multiplication, I have cos t of x1 t, cos t of x2 t. Okay, this is nice. This is y1 plus y2. Okay, so here if I just write this, right, this is x1 of t plus x2 t. What the system does is system multiplies x1 of x1 plus x2 with cos t and gives me the same thing as I would expect. Okay, nice. Similarly, you can just check is y equal to x square plus sin x. I do the same formula or the same recipe. y1 is x1 square plus sin of x1, y2 is x2 square plus sin of x2. I add y1 plus y2. Instead, I just give both inputs together. I have x1 plus x2 as my input. The output Okay, the first term is a sinusoidal term with the total input, and the second term is x1 plus x2 whole square. Okay, let us expand this. So, this will be x1 square plus x2 square plus twice x1 x2 plus sin A plus B. Okay, I am assuming I remember the formula, sin A cos B plus cos A sin B, okay, something like this. Okay, I may be making a mistake, but just verify this. But what is definitely sure is that this, and if I just say take the, is this term here equal to the sum of these two terms? Well, this is actually not true. So, here I am saying that this there does not exist a similarity here. So, y1 plus y2 is not equal to x1 plus x2 whole square plus sin x1 plus x2. So, it is not a linear system, and this is a linear system. The answer is a linear system. Okay, nice. So, systems which were satisfying homogeneity and superposition, we put them in one basket, we gave them a name called linear. What do we do with the others? Oh, let us see if we can see something like that. We all would have come across some diode. The behavior of a diode is given by this expression. I am not here to, so we will not discuss too much into the dynamics of or how the principles of working of a diode. What I know is that the current voltage relation satisfies an exponential curve like this. So, Is is the saturation current, Vd is the voltage across a diode if I take the circuit, Vt is some internal thermal voltage, N is the identity factor, and so on and so forth. Okay, so is the relation Vd to Is linear? Okay, I think I leave that as an exercise to say that it is actually not. Okay, does an ideal diode satisfy superposition homogeneity? Just quickly check that the answer is no. Okay, and then what happens when I put, so if this circuit, if I have some voltage source, this I know is linear. I also know that if I put another inductor here, this is also linear. What happens when I put a diode? Okay, I ask myself a question, what happens when instead I have a diode here? Okay, so I look at the principles of the working of diode, that I keep on increasing the voltage till it reaches this threshold. The current will be 0. After that, you see that the voltage builds up, the diode gets activated, and then there will be some current flowing through this diode based on also the value of the resistance, which is 1 kilo ohm. And this is, you can see there's a little bit of a nonlinear behavior here. If I checked here, this curve was just kind of a nice straight line through the origin. Okay, and then that is essentially a line of the form y equal to mx, and these are also of the same nature, right? Q equal to cv, f equal to ma, and so on. Okay, so where are we after all this, right? So the output, if I were to say summarize, the output of the linear system varies linearly with input. The graphs will have straight lines, as I just showed. Graph here has a straight line, and here, well, it's not a straight line. So what happens is the graphs will have curves, it will have discontinuity. So you could also have graph of this form is nonlinear. There's a discontinuity here, there's a discontinuity here. Graphs of this form are also nonlinear. Things which saturate, right? So you have maybe things which start here, they increase, and then this is also nonlinear. So graphs will have curves, discontinuities, and so on. Superposition and homogeneity hold, superposition and homogeneity do not hold. I claim that these are easy to analyze, and the nonlinear systems may not be very easy to analyze. We will see that eventually during the course. Also, something which we will leave for later is that the linear system will have unique equilibrium points in most cases, where nonlinear system is a little more complicated. It may have a possibility of multiple equilibria. Okay, so we somewhat talked about the simple interest, right, where the interest was PNR by 100. Again, if I remember the formulas from school correct. And if I plot the interest versus a time here would be in a scale of month or year or whatever, you could see a good relation there. What happens when I do a compound interest? When I plot the interest, okay, just try to do this exercise, right? The time versus the interest, plot the simple interest, plot the compound interest, and check if the simple interest satisfies homogeneity and superposition, or the compound interest satisfies, or none of them satisfy. All those binary combinations are possible in this case. So, we gave different names now to systems: static versus dynamic, linear versus nonlinear. Of course, there could these are not like that, you know, they are in different baskets. So, say suppose in this box there is static, in this box there is dynamic, in this box there is linear, in this box there is nonlinear. There could also be systems which are static and nonlinear. There could also be systems which are dynamic and linear. There could be static linear systems also. There could be dynamic nonlinear systems also. So, maybe I will just quickly write down some examples. Static plus linear, y equal to mx. Okay. Static plus nonlinear, y equal to cos x. Okay, what is pending? Dynamic plus linear. Okay, that was the simple RL circuit, V equal to L di by dt plus Ri. Dynamic and non-linear, I could just write dx by dt is x square, or the other example that we saw where we had dj by dt whole square. Okay, so these are not like all say in different buckets. So these combinations are also possible. What is not possible is these combinations. Sorry. What is not possible are directly these combinations. The system cannot be both static and dynamic at the same time. System cannot be both linear and non-linear at the same time. We will see next in the next lecture, are there further classifications possible. Okay, stay tuned. Thanks for listening.